Everybody hear me? All right, so I'm Vick. So today I'll be presenting some work with Sammy Thomas. Sammy's in the back there. And so we worked on this project called Hatching Theory Instantiations with Yardbird, forgive the cutesy name, but this is about finding bounded model, or doing bounded model checking with EGRAPHS'. So just as a general overview, I'll motivate sort of why we wanted to work on this problem. Then I'll talk about guidance in SMT solving. I'll give a bounded model checking example. I'll talk about how we use EGRAPHS', and particularly how we use EG. We'll see a cost function comparison, and then I'll talk about conclusions and future work. So right, introduction and motivation. So as a rule, SMT solvers struggle with quantified reasoning, but quantifiers are, we want to use quantifiers to reason about things like arrays and distributed protocols. And so this talk is going to specifically focus on proving bounded properties of arrays in software. So the difficulty for SMT solvers lies in how they choose to instantiate quantifiers. And so the big question is, how do we know which terms are useful? And so we're going to tackle this by using user-defined cost functions or using the cost functionality that EG extends to supply domain-specific information to the instantiator. So guidance in SMT solver. So SMT solvers generally allow syntactic guidance. Like in Z3, you can supply what terms you want to, or what terms you would prefer the underlying SMT engine to use in particular quantifier instantiations. But EG's cost function framework allows finer grained guidance. So we can do we can do a semantic analysis of our terms, and it gives us finer grained control over which terms to instantiate with. And so the main point of this work is to compare Z3 with our tool Yardbird on bounded model checking examples. And so just generally, we can, the main takeaway is that our tool is faster than Z3 on 50 benchmarks, so we have about 200 benchmarks. And so we're faster than Z3 on 50 benchmarks, and it uses fewer instantiations on 94 benchmarks, which is about 50% of the total. So that's sort of the main takeaway, is that it really helps you in SMT solving to use, to have specific guidance in your problem domain. So here's the technique overview. So we're going to start with a Rust program. It doesn't have to be a Rust program. We just we have a macro system that translates Rust into our sort of logic language, which is VMT. And if you've seen SMT-lib, VMT is very similar. Then we're going to abstract the array theory, since we're dealing with arrays. And I'll get into what exactly I mean by that in a minute. Then we're going to feed the abstract program into Z3. We'll get an abstract counterexample. We'll feed that into EG. And then we're going to extract refinements, and again, I'll define all this a little bit later. But sort of the key is we're going to extract refinements with a particular cost function. So here's a Rust example. This is a very simple example of the typical types of programs that we're going to be doing bounded model checking on. So you can see this is array copy. We're going to take vector A and a mutable vector B and some loop bound in, and we're just going to copy the array A into the array B. And of course, we all know that this property holds at the end of this loop. So every index of A is equal to every index of Z. But how do we check this property? How do we verify this property? So we can do it in a bounded way using bounded model checking. And so the general framework is we're going to translate that Rust program into logic. We're going to unroll the loop in time. So if we want to do a bounded model checking to depth 20, we're first going to unroll to depth 1, 2, 3, 4, and so on. And we're going to check that the property is true at every step of the unrolling. So this is pretty simple to do in Z3 if you use the full array theory, and it's definitely simple if you are just trying to prove very small programs like the one I just showed. But it can take a long time if you're going to try to prove more interesting properties of slightly more difficult programs. And so what do I mean by the full array theory? So here are the axioms of array theory. So all these capital variables are implicitly universally quantified. And we don't have to go over exactly what these mean, but this is just kind of the general structure, and all of these will be encoded as rewrite rules inside of EG. So abstraction and refinement in BMC. So how we can think about abstraction at sort of a high level is that we want to forget facts about the array theory using uninterpreted functions. So we're just going to forget all of the sort of interpretation of the array theory, and we're just going to use uninterpreted functions, and we're going to sort of add back in only the facts that we want the solver to know about. So we're going to worry about instantiating those quantifiers. And of course, this removes the need for quantifier reasoning in the SMT solver, at least at the array level. And so yeah, what I mean by refinements are just array axiom instantiations using program terms. So we can see like this is an example of an instantiation that egg might find in a typical bounded model checking loop. So refinement generation. So yeah, so this is now kind of getting into how we use egg. So we're going to build the eGraphs in egg from the SMT solver model. So we're just going to put all the interpretations of the variables, all the interpretations of the program terms into the eGraph. We're going to saturate the eGraph with the array axioms. And then, so this is kind of a weird way to use eGraphs. I don't know if this particular thing is usually done, but separation will stop if two E-classes will be merged by rewrite. So we don't want to start merging E-classes after the original eGraph is built. And why we don't do that is because this signals a gap in solver's abstraction. So if we're going to use an array axiom to merge two E-classes, that means that our original Z3 model didn't know about that particular fact of the array theory. We're going to add it back in. And so we can just immediately use that rewrite that egg gives us, but we're going to, there's no guarantee that that refinement is going to be good. So there's these raw refinements that come out of the egg are not guaranteed to be useful. They might be useful, but we're going to minimize the refinement cost using the custom cost functions. So we're going to use cost functions to prefer, quote unquote, better terms in refinements for some definition of better, and I'll get into what I mean by better on the next slide. But yeah, so again, egg's cost function framework allows us fine-grained semantic control. So we can do things like, look at a term and, compare terms with other terms in the model and, do sort of fine-grained control on this particular, problem domain. And so this differs from traditional SMT solver term selection in that we're not just going to pick from a static bag of terms. We're actually going to, sort of do some sort of semantic evaluation of them in the cost function. So I used two cost functions in the evaluation. So the first is AST size. So this is just a very naive implementation of a cost function. We're just going to prefer small terms to instantiate those quantifiers. And this is likely going to miss opportunities for generalization. So to kind of get a sense of this, you could think that we might instantiate a quantifier with the constant term 0, where actually we would want to use some more complex term like selective A at some particular index. And that's going to be the key to allow us to move forward in the proof. But with the AST size, we're just going to plug in the smallest possible term, and we'll likely diverge at that point. And then we have this slightly more complex cost function called the property-directed cost function. And so this prefers terms that are in the property check or that are later in the bounded model checking trace. And this is likely to miss important constant terms. Small constant terms we'll probably forget about. But since it leverages the problem structure of a bounded model checking problem, it's likely that it will perform better, and we'll see the results bear that out. So here on the left-hand side, we have Z3 runtime on the x-axis, and then we have Yardbird runtime, which is our tool, on the y-axis. So we can see anything below the x equals y line is where we do better. So you can see for AST size, for that naive cost function, we're doing pretty awful. Z3 is sort of dominating us on all of these problems. And then here is a graph. Instead of runtime, I've plotted the number of axiom instantiations that we had to add and the number of axiom instantiations that Z3 used to prove the same property. So again, Z3 is using fewer axiom instantiations than us, and it's beating us on all these fronts because we're using this naive cost function that doesn't leverage problem structure. But when we have this property-directed cost function, you can see that the runtime cost is getting much tighter around the x equals y, and then for this particular for this metric of number of axiom instantiations needed, we can see that we're actually starting to outperform Z3 by quite a large margin on about 50% of the examples. So it's kind of interesting, and kind of to give some sort of rationale for why this metric was included. I just thought it was kind of interesting to include something where we can actually see some improvement over a super highly engineered SMT solver like Z3's, because we didn't do much optimization on our tool, but we were still able to see we were able to beat Z3 on about 20% of those benchmarks, and 50% when we used this kind of maybe a little bit contrived metric. But yeah, so the conclusion is that user-defined cost functions can beat Z3 without optimization. Like I said, we did not try to optimize our tool, but we were able to beat Z3 on some number of examples. And we can see that property-directed is better than AST size for this particular. That's kind of unsurprising because we're leveraging more problem structure. But there are still cases where AST size dominates property-directed, for one particular example, this array split 11. The property-directed cost function diverges. It chooses some term that it shouldn't have, whereas the AST size finds a small proof for a bounded depth. So these are still just heuristics. They're not. It's not a one-size-fits-all solution. You're still going to have to care about different cost functions for different problems. So future directions, yeah. So further improvements to cost function guidance. So just trying to make better cost functions for these problems is kind of an interesting area. Trying to beat Z3 on a larger number of problems. And then dealing with other theories is also interesting. Abstract data types specifically, we could kind of do bounded model tricking on more problems, on a specific problem domains. That would be interesting. And then integration with inductive invariant generators like IC3IA. So we could extend, so we could do a bounded proof up to some depth, and then using the instantiations that we found to get a bounded proof, we might be able to supply guidance to an unbounded proof generator in the case of inductive invariance. And then we could integrate history and prophecy variables. This is some of my previous work that this is kind of a quantifier elimination technique. But I haven't implemented that yet in Yardbird. And then also, I was thinking it might be interesting to supply guidance to theory explorers like Enumo. I don't know if this is totally off base, but it would be kind of interesting. If we found a rewrite in Enumo, maybe we could try bounded model checking with that rewrite, and so kind of prefer rewrites that allow you to get further in bounded model checking. But again, I'd love to be corrected by that if someone knows more about that than I do. But yeah, thanks, and happy to take any questions.
Thanks for the great talk. We have plenty of time for questions.
Yeah, thanks for the great talk. Can we go back to the summary, right?
To the what?
To the conclusion.
Oh yeah.
Okay. So if you during your design of the cost function, what was the most important thing you have to consider to apply to the cost function? Which information was the critical part of the
Right. So, it obviously helps to have experience with bounded model tricking problems. So, in proofs, it's just likely that terms that appear in the property will be helpful in proving that property. And so that was kind of the most key thing, is to prefer those property terms in your term selection when you're instantiating quantifiers. But, there may be other things. I haven't fully explored that. Yeah.
Do you think there is a kind of a universal cost function that can help everything?
Definitely not. We saw that even this AST size cost function will beat property directed on some amount of the problems. It's just the problem is too difficult. The search space is too large to have a one size fits all cost function. It's just not going to.
Could we imagine a system that can evolve the cost function automatically from the simplest one like AST to fine-grained?
I think you definitely could. Another thing I thought about was kind of running cost functions in a portfolio sort of way, and just sort of picking the best instantiation. Or I guess now you have to have a second order cost function to pick the best instantiation from from the cost functions. But you could just run them in parallel and just say, if this particular cost function happens to find a proof, then that's fine, and if another one does, that's also fine.
Okay, thank you.
Hi, given a problem, can you cheaply decide if your tool is going to work better or if C3 is going to work better, so you can build a portfolio solver?
Right. So I think, when we look at something like this, I was trying to find some sort of pattern in the problems where you could say, this particular problem is definitely going to work better on our tool, and then this other problem is going to work better in Z3. I wasn't able to do like a full analysis of that, but one thing I did notice was if there's theory combinations. So if you're doing a lot of multiplication in the loop, and they have all these array tiling examples where you're doing something like that, then the abstraction of the array theory kind of helps Z3, from my experience, kind of explore that theory space. And then, just by supplying, maybe a few array instantiations, you might be able to find a proof faster. But I've also seen the converse. So I haven't been able to draw a strong conclusion about when this technique will work or when it won't. That would definitely be an interesting, thing to find out.
Great talk. I wondered if there's something special about the theory of arrays that caused you to focus on that, or would this work for bit vectors, or choose your favorite, some other thing?
Yeah, I mean, I was just familiar with the theory of arrays. Some of my past work has been on that, and I had this nice benchmark set that allowed us to kind of, get some examples running quickly. But I think so. It has to be axiomatizable in this sort of, like the theory of arrays is nice just because it has a very small axiomatization, and that like these are very easy to encode as rewrite rules. So like in the theory of bit vectors, I'm not sure if you could. I mean, I don't know for sure, but yeah, I don't know if it's as easily sort of translatable into this. But I mean, that would be. I mean, that's kind of what I was thinking about with like ADTs. Is maybe there's some way to encode the problem like that, but I don't know.
Okay, let's thank the speaker one more time.